Lesson 3 is inverse functions, and in 3.1 we're going to get into just the inverse of a general function, and then in 3.2 we're going to talk about the inverse of an exponential function. So before we get into inverse functions, I want to review inverse operations. So inverse operations are operations that undo each other, like addition and subtraction. You know, if you were to like add 4 but then subtract 4, you would end up at your original number. And then multiplication and division have the same effect. They undo each other. If you were to like multiply something by 2 but then divide it by 2, you would end up back at your original number because they're inverse operations. And then functions can have inverses too. Inverse functions just kind of basically work in reverse. So I'm going to just create like a little picture to go along with that. So it's not a square, it's supposed to be. Okay, so if we picture this is our function, it's kind of like a machine. We have our input that we put in the function. I'm going to call it f of x. And then it spits out our output, whatever that may be. If we find the inverse of this function, it's going to take our output and put that in the inverse and spit out our input. So it just works like completely in reverse of the original function. And then back to kind of this section of the definition. So because not all inverses of functions are still functions, meaning they just don't follow that certain set of rules, you may see them referred to as inverse relations. And relations are just kind of like the relationship between the two sets of numbers, but they don't have to follow as many rules as functions. So functions, you have to have, each input can only have one output. If it doesn't follow that in that rule, or like it doesn't follow that rule specifically, we just call it a relation. Okay, so for finding inverses of functions, there's like a set of steps that you can follow. That's these steps over here, finding inverse functions. I'm going to go through each step and try to kind of like code them a bit in these current examples, or in these next examples. But step 1 is replace the function notation with a variable. For example, change f of x to y. 2, switch the places of x and y. 3, solve for y. And then 4, change y to that like f with the little -1 exponent of x. You don't really read it like that. It's not like a -1 exponent. It's actually inverse, and like the inverse of f of x. So we'd say inverse of f of x is how you would read it. Okay, so for example 1, find the inverse of each function. So for A, step 1 is replace the function notation with a variable. For example, change f of x to y. So example 1a is f of x equals 3x plus 6. So step 1 is to take f of x and replace it with y. So instead of f of x, it'd become y equals 3x plus 6. So we're done with step 1. And then step 2, switch the places of x and y. So that means like y is right here, x is right here. We're just going to swap them. Everything else stays the same. We just switch the location of x and y. So then that would become, instead of y equals, it would be x equals, and then 3y plus 6. And then step 3 is solve for y. That means get y by itself, isolate it. So usually when we're solving, we have to undo addition or subtraction first, most of the time. So I'm going to cancel out that plus 6 right here. The opposite of adding 6 would be subtracting 6. So I have to subtract 6 from both sides. And then this would become x minus 6 equals, bring down my 3y. 6 minus 6, that would be 0, and cancel out. And then still trying to get y by itself. So now there's that 3 that's being multiplied by it. So to cancel out multiplying by 3, I would have to divide both sides by 3. And I would have to divide this entire side by 3. So the 3 divided by 3, that would cancel out, and it would leave me with just the y on the right side of the equal sign. And then over here, I'm going to divide each term by 3. So it'd be like x divided by 3, which is just like 1x divided by 3. So it'd become 1/3 x. And then the second part would be -6 divided by 3, so that would be -2. So we have y by itself, so we're done with step 3. Step 4 is to change y to the inverse of f of x, and we also want to write that part first with like it in front of the equal sign, or to the left of the equal sign. So it'd be the inverse of f of x is equal to 1/3 x minus 2. So the inverse of f of x equals 1/3 x minus 2. Okay, and then for the similar problem, just like different numbers. So I'm going to go through those steps again. So step 1, for the function, it's f of x equals 1/3 x plus 2/5. Step 1 says replace f of x with y. So f of x is right here. I'm going to take it out and put a y there instead. That equals, everything else stays the same. So 1/3 x plus 2/5. And then step 2, switch the places of x and y. So we have our y right here, and then y is right here, x is right here. So if we want to switch their places, the equation or the function would start with x, so it would be x equals 1/3 y if they switch, plus 2/5. So we're done with step 2, and then step 3 is to solve for y, meaning that we get it by itself. Same thing here, if we can, we usually undo addition or subtraction first. So that plus 2/5 I would need to cancel out by subtracting 2/5 from both sides. So then on the left, this would be x minus 2/5 equals, bring down the 1/3 y, and then 2/5 minus 2/5 is 0, so that cancels out. I still need to get y by itself, so now there's that like 1/3 that's being multiplied by it. Usually to undo multiplication we divide, but we don't typically divide by fractions, like dividing by a third. So instead of that, I can always multiply by the reciprocal. So if I multiply by the reciprocal of 1/3, that would cancel it out, which the reciprocal of 1/3 is 3. So I'm going to multiply both sides by the reciprocal, which is 3. What that's going to do to the 1/3 is 1/3 times 3 would just be 1. So this would just be like a 1y, but we don't need to write the 1. We just want the y by itself. And then I am going to go ahead and distribute in that 3 to the x minus 2/5 to simplify. So 3 times x would be 3x. And then 3 times negative 2/5, because we're multiplying, we don't need a common denominator. We just multiply the numerators together. So it'd be 3 times negative 2, which is negative 6, and the denominator stays the same, so negative 6/5. And then now we have y, not what I meant to do. Sorry, I just want to scoot it over. Now we have y by itself. So like we've solved for y, we're done with step 3. We can move on to step 4, which is just change the y into the inverse of f of x. So it'd be the inverse of f of x equals all of this. So 3x minus 6/5. So as soon as you get y by itself, that means you have solved for y, and you just need to rewrite the like inverse with inverse notation, and also just with the inverse of f of x written first, like to the left of the equal sign instead of on the right. Okay. So for C, this would be a good one to try on your own. Even if you can't, like, if you're not sure at the beginning, you can pause it throughout the video or throughout the example and see if you can finish it out on your own. I'm going to go through the same set of steps though. So C is f of x equals x over 2 to the 3rd power. So step 1, replace f of x with y. So y equals x over 2 to the 3rd power. So we've switched out f of x for y, and then step 2 is to switch the places of x and y. So instead of y equals, it'll be x equals, because these are going to swap. So x equals y over 2 to the 3rd power. And then now we can move on to step 3, because we've switched the places. We're done with step 2. Step 3, solve for y, so that means get y by itself. So before I can even begin to start to get y by itself, I have to figure out a way to cancel out that exponent, because it's really like kind of like caging it. So if I want to get rid of the 3rd power, I need to use the inverse of that, which would be the 3rd root. So I need to cube root or 3rd root both sides. So then this would just become the cubed root of x. And cubed root just means the 3rd root, or a root with an index of 3. And then on the right side of the equal sign, the 3rd root and the 3rd power, those would just cancel each other out. and it would just leave us with the y over 2. So now we're trying to get y by itself, and now that the cubed root is gone, or the cubed exponent, the third power is gone, we can drop the parentheses. And I just have that 2 that's in the denominator, so that's kind of or it is y divided by 2. So to cancel out dividing by 2, I would multiply both sides by 2. So then this would become 2 times the cubed root of x equals, and then the multiplying by 2 and divided by 2, that would cancel out, so it'd be equal to y. So we have y by itself. That means we've solved for y and we're done with step 3, and we can move on to step 4, change y to the inverse of f of x. So it'd be the inverse of f of x equals 2 times the cubed root of x. Okay, so biggest thing, save this set of directions for finding the inverse so that you could always refer back to them for a checkpoint or an exam. And then for example 2, there's not a whole lot to do for this example. I just kind of wanted us to notice something. So example 2, examine the input and output tables for the function from 1a and its inverse. So this first table is f of x equals 3x plus 6. It's the input output table. So if I were to put -1 into that function, I would get out 3 and so on. And then this is the inverse function, is the inverse function from that same problem. So the one on the left is the original, the one on the right is the inverse. So when you're looking at input output tables, the top row is the domain. It's all of the input values, and then the bottom row, or it could be left and right if it's vertical, but the bottom row would be the range. So if we look at these two tables and we kind of see how the domain and range, or the input output values, have switched, you may hopefully notice something. But if we look at, for example, -1, 3, over here on the inverse, it's 3, -1. The input output switched. Right here, 3, 15 switched to 15, 3. So I had a hard time saying that. And then right here, 10, 36 switched to 36, 10. So it goes back to this little kind of picture that we drew up here, where if you have a function, yes, you put in the input, you get in, or you get out the output, the inverse would take the original output, put it in, and give you the original input. It switches the order. So that means that when you have a function and its inverse, the domain and the range switch, or the input and output values switch. So domain and range switch. Okay, so one more time, if anytime you have an original function and its inverse, the input and the output values will switch, their domain and ranges swap. So for an example would be -1, 3 became 3, -1. Okay, moving down to 3.2, this is the inverse of an exponential. So the inverse of an exponential is called a logarithm, which we don't really say that full word all the time. We usually just call it a log. So log for short. So most time, if not every time from here on out, you'll hear me call it a log. But what logs do, and just actually a quick refresher, I'm gonna add an exponential. It's what we've kind of been studying in this chapter, this unit, is if you have a function that has a base with a variable exponent, so 3 to the x power, or 1/2 to the x power, anything that has a variable exponent, not necessarily something that would have a regular number exponent would be classified as an exponential function. But the inverse of an exponential is a log, and then the goal of a log is to isolate the exponent from an exponential. And I will say sometimes when we're evaluating logs, you will see exponents that aren't just variables, but the purpose of the log is to kind of isolate and solve for an unknown variable. Okay, so there's a couple forms that you like really want to get familiar with like as quickly as possible. So I would like maybe make a note card for it. The one on the left, this is called exponential form. And then the one on the right, this is called log form. And those are essentially two different ways of writing the same exact equation, just in different forms. So if I have exponential form, it's b to the x power equals y. Log form changes it to x equals log base b of y. I'm going to add that really quick. And this is like, it's always weird trying to figure out how to read it for the first time or read math for the first time. So this is log, let me see, wherever I have the most space. Up here, this is log base b, this little guy, of y is how it's read. Log base b of y. Okay, so now I want to kind of show you like where each thing gets rearranged to when you're switching from log form or from exponential form to log form. And then we'll do a practice one, which is kind of regular numbers because it's always a little bit easier that way. Okay, so this b is the base of the exponential and it becomes the base of the log, this little b. And then the purpose of a log is to isolate the exponent from an exponential. So the exponential form, the exponent is x. And when you go over to log form, that's the part that's by itself. It's isolated. And then the last little like thing that doesn't really have like a name for it, unfortunately, is this y, and that becomes like what you eventually take the log of over here. So this pattern, like you want to get comfortable changing between these two forms of, you know, like the exponent from the exponential becomes by itself on like the log form. The base of the exponential becomes the base of the log, and you'll see the word log written in there. And then what the exponential was originally equal to becomes what you were taking the log of. So again, highly, highly recommend like making a note card or just like having a sticky note with this on there so you can refer back to it. Okay, so now if I wanted to rewrite 4 squared equals 16, which is a true statement in log form, we could use that same pattern. So like logs are going to isolate the exponent, so the 2. So the 2 is going to go right here by itself. And then it's going to be equal to logs. We're changing it to log form. And then the base of the exponential, the 4, is going to become the base of the log. So we'll put a 4 right here, a little 4. And then what was like the power originally equal to, the 16, is what we're taking the log of. So that goes here. So 16. So it's 2, this is read as 2 equals log base 4 of 16. Okay, so the next little part, and it's going to kind of help us like bring everything together. And again, this is like the very, very intro of logs, so we'll get a lot more practice with it. But when you evaluate a log, you're asked which exponent takes you from the small number, which sounds silly to say, but is referring to the base, to the large number. So if I look at like this version, I'm going to actually just copy it down really quick. So which exponent takes you from the small number to the large number? So the small number is referring to like the base, that little baby 4, and then the large number is referring to that 16, like the one that's literally just written bigger next to it. So it's asking which exponent takes you from 4 to 16. Which exponent takes you from 4 to 16, meaning like 4 to what power equals 16? Well, if we take 4 and we raise it to the second power, that would equal 16, which is why the like log is evaluated and it equals 2. Because 2 is the exponent that takes you from 4 to 16. It takes you from the small number to the large number. Okay, so logs, I know the first time I learned logs, I was like a little frightened, but we'll get much more practice with it. So that's just a little baby intro. Okay. So the reason that we need this for this section is because we're going to be writing the inverse of an exponential function, which the inverse of an exponential function is a logarithm. So this part right here is just the same forms that you had written like up here. This is the same as this, so if it's on your page, you don't necessarily need to rewrite it. If you had to go to a new piece of paper, though, you may want to rewrite it. Okay, so exponential form, I'm just going to go through and kind of like recolor code it the same way so we can refer back to it the same way, but exponential form versus log form, again, they're the same like equation, just kind of restructured. So the base of the exponential becomes the base of the log. The exponent from the exponential becomes like what's by itself in log form. And then what the exponential was originally equal to is what we're taking the log of. Okay, and then this set of instructions is the same set of instructions as we had when we were finding the inverse of like the kind of just regular functions. We're going to follow those same steps here. So example 1, find the inverse of each function. A is f of x equals 7 to the x power. So the first step, replace function notation with a variable. We're going to take f of x out and replace it with y. So y equals 7 to the x power. So we did step 1. Step 2, switch the places of x and y. So we switch x and then we switch y. So then it would become x equals 7 to the y power. And then step 3 is to solve for y. So we're trying to get y by itself. We don't really have a way of doing that, except now we can just restructure the equation. So if we like look at these two forms right here, we're trying to get this exponent by itself, the y, which is exactly what happens when we switch from exponential form to log form. So that's what we're going to do. So for like solving for y, if y happens to be an exponent, we have to switch forms, because that's the only way to free up that exponent. Okay, so I'm going to go through and just kind of like label them in the same colors as our exponential and log form formulas. So in the like exponential, the number that was like what the exponential is equal to, that was the blue one, just y, like referring to up here. It's just kind of like the equation is switched in a different order. And then the base of the exponential, that is 7. That was like the b up here. And then the exponent itself is y, and this problem up here was x. So when we go to rewrite it in log form, the exponent is what's going to end up by itself. So the y this time is what's going to end up being by itself, and that's equal to log. And then the base of the exponential is going to match the base of the log, so this would become a 7. And then what the exponential is originally equal to is going to be what we're taking the log of. So that x is what we're taking the log of. So then now this is read as y equals log base 7 of x. And we have y by itself, so step 3 is done. And we can move on to step 4, which is just to change y into the inverse of f of x. So the inverse of f of x is equal to log base 7 of x. So inverse of f of x equals log base 7 of x. As you get more comfortable with this, this will be as straightforward as it looks like, because if you look back at the original problem, it's f of x equals 7 to the x. So if you have an exponential with a base of 7, the inverse will be a log with a base of 7 and nothing else funky going on. When you have other parts of the original function, like how this has a -4, it's not quite as straightforward. But if you ever saw like something as simple as this one, you could kind of start to recognize that pattern. Okay, so for b, f of x equals 10 to the x power. So step 1, replace function notation with a variable. So we'll change f of x out for y. So y equals 10 to the x minus 4. And then step 2 is to switch x and y. So then it would become x equals 10 to the y minus 4. And then step 3 is to solve for y. So we want to get y by itself. I will say before you want to change forms, you would like your exponential, in this case the 10 to the y, to be as isolated as possible. So I want to cancel out that -4 first. So in order to cancel out -4, subtracting 4, I'm going to add 4 to both sides. So then this becomes x plus 4. And then equals 10 to the y. And then now we're trying to get y by itself. So that's when we have to change it into like log form, because we're trying to free up the exponent from an exponential. So if we switch the form, that means that we take that exponent and it goes by itself. So y equals, and then we're changing it into log form. The base from the exponential, in this case it was 10, becomes the base of the log. So log base 10. And then what the exponential was originally equal to is what we're taking the log of. Because this has more than one term, like there's an x and a +4, I would have to put it in parentheses. So x plus 4. So one more time, the like exponent from the exponential, the y, is what gets isolated or by itself when you put it in log form. And then log is just kind of always written in log form. And the base from the exponential, the 10, becomes the base of the log. And then what the exponential was originally equal to is what we are like taking the log of. So that's kind of the last thing that's to place. So altogether it's read as y equals log base 10 of x plus 4. And then we can move on to step 4, because now we have y by itself. Step 4 is to just rewrite it with that inverse notation. So the inverse of f of x equals log base 10 of x plus 4. So inverse of f of x equals log base 10 of x plus 4.